All right, so here will be a quick application example that involves a chain rule. Okay, so I've made my videos already to address when and how to use the chain rule. And now I have a word problem that's based on the kind of modeling that they do in economics. Okay, so before I talk about the problem, let me give you a hint real quick about something that we'll need to know to do this. If you hear verbiage like inversely proportional, here's how we have to understand it. If we say, for example, that y is inversely proportional to x, then that means y is equal to k divided by x, and then k is equal to some constant, okay? And that constant would depend on the situation, but in general, that's the equation that we get. All right, so we say like that often you'll find that things are either directly proportional to each other, meaning that if one goes up, the other goes up, or inversely proportional to each other, meaning if one goes up, the other goes down. And so we might hear a statement like this sometime. Okay, the value v of an item is inversely proportional to root 2t plus 1. And already I can say, well, that means if this number goes up, like say if time goes up or time advances or time passes, that means the value is going to go down. All right, and that would make sense because for most things there is depreciation over time. They become less valuable over time. All right, so the value v of an item is inversely proportional to root 2t plus 1, where t is the number of years since purchase. Okay, so as far as our units go, let's say that v is the value in dollars and t is the time since purchase in years. Okay, can you find the function v is a function of t, meaning a formula where I can plug in the time since purchase and calculate the value at that time if the initial value of the item is $8,000? Well, so let's do that this way. I have an equation that I think makes the starting point for this. For one thing to be inversely proportional to another. So if you tell me the value v is inversely proportional to this item, root 2t plus 1, then that's the basis for our working equation, all right? It's just an issue of figuring out what that number is supposed to be. All right. So it says, in addition, though, that the value initially is $8,000. Okay, so that means that if t was 0, k would be it would have to work so that that number was 8,000. Okay, so let's use that. So 8,000, that's the value whenever t is 0. All right, now if t is 0, 2 times t is 0, and that's going to look like this down there. Okay, all right, v is 8,000 when t is equal to 0. I put that into my working equation, I end up with this, and that tells me that k is 8,000. All right, k is 8,000. So now I have my equation that gives the value as a function of time. Okay, it's going to be 8,000 divided by root 2t plus 1. So we've got that. V is equal to 8,000 over root 2t plus 1. Okay. All right. Now, so next part. We might hear something like this. Calculate the rate of depreciation if t is 1 versus if t is 4. Okay, what's the rate of depreciation? Let's think about like this. The value we would expect is getting less over time. The value of an object, a car, a piece of machinery, most things, all right, not everything, but most things, becomes less over time. So we might say that, well, it becomes less over time, but how fast? Like how many dollars per year less valuable does it get? All right, that's what we mean by rate of depreciation. So the rate of depreciation is just, therefore, the derivative dv over dt, the derivative of the value with respect to time. And why would I say that? Well, think about the units of this. What are the units of v? Dollars. And what are the units of t? Years. So this is how many dollars per year the value is depreciating or decreasing, okay? So that's all the rate of depreciation is. I'll say a little bit more about it in a little while. I'll show you something else once I get my answers to the problem. Okay, so I'm looking for the derivative of this, it turns out. So let's do like this. Let's write v as 8,000 times 2t plus 1 to the negative 1/2 power. And then the rule to find the derivative of this is the chain rule. I'll carry this constant down, multiply it by the derivative of that, and by the chain rule, that's going to be negative 1/2 2t plus 1. I've got to subtract 1 from that, so that's negative 3/2. Then times the derivative of this inside thing here, and that's 2. Okay, so what's that end up being? dv over dt is, well, the 2's cancel. I'll get a negative 8,000, negative since the value is decreasing over time. And then down here I'll get 2t plus 1 to the 3/2 power. Okay, so that will calculate the rate of depreciation. This will calculate how fast the value of the item is decreasing. Okay, so okay, let's put that down. I found dv over dt to be negative 8,000 over 2t plus 1, 3/2 power. And then I'm comparing what the rate of depreciation is when t is 1 versus t is 4. So here's something that we can expect. Like with, say, cars, for example. They lose most of their value right at the beginning, all right, generally. So maybe not all the time, who knows, but that's generally the way things work, okay? And then over time, they tend to maintain their value a little more if they're taken care of. So that's what I'm thinking here, is that with this being a proper model for the value of a typical item, that it will decrease in value, but it will lose most of its value at first, and then it might steady a little bit over time. It still loses value, but not quite as fast as it did originally. So I would expect when I calculate dv dt when t is 1, that is like a much bigger number, losing value faster than when I calculate dv dt when t is 4. Okay? All right, so this is going to be what? If I put 1 in, I'll get negative 8,000 over 3 to the 3/2 power. Okay, so that turns out to be negative 8,000 divided by 3 power 3/2. So that turns out to be 1539.6. All right, I'm going to have to do some rounding, but negative 1539.6. And what are the units again? The units of a derivative are the units of this variable on the top over the units of the one on the bottom. Well, that's dollars and years, right? Okay, so that's how we can understand this number. So that's dollars per year. So 1 year after purchase, it's losing its value at about $1,500 per year. Okay? What about at 4? Okay, so at 4, I'll get negative 8,000. And then if I put 4 in here, let's see, that's 8, 1 is 9. So that's going to be 27. Okay? If I take 9 to the power 3/2, that's what I'll get. So negative 8,000 divided by 27, that's going to be 296.30 with some rounding. Negative 296.3. Again, it's going to be dollars per year. Okay? All right, so those are the rates of depreciation. It's losing value slower, a little slower as it ages. And that's, not, an unbelievable thing to happen. All right? Okay, so that's my commentary here. Losing value much faster. I guess when you really compare those numbers, that one's quite a bit bigger. All right. Now, let's try to tie it all together. So here, I have the curve. It looks a lot like that. This is not a scale graph or anything like that, but it looks like this. It descends in roughly this manner. V is 8,000 over root 2t plus 1. And remember how we also said the derivative is the slope of the curve? Well, it's like saying the slope there is negative $1,539 per year. That's the rise over run there if you consider the units. The rise, well, that has units in dollars, and the run has units in years, okay? And at this point, when t is 4, the slope there is negative $296.3 per year. So again, it's the rate of change, the rate of depreciation. That's one way to look at the derivative. If you say it's the slope of the curve, it also turns out to mean the same thing, all right? So whether it's the slope of the curve, the rate of change of v with respect to t, we can apply the same meaning to it no matter what.